Alright, this tutorial is for physics for Monday, December 14th. When last we left our physics heroes, we were looking at sample problem 4A from page 132 in your Holt Modern Physics textbook. So go ahead and get that together. What we've established so far is that we have an object sitting on a sloped surface. The surface is sloped at 35 degrees, and in order to most effectively deal with this, the easiest way to do this is to tilt the axis so that our x-axis now is parallel to the surface and our y-axis is perpendicular to the surface. With that, I'm going to get rid of the axes. Now the other things that we had already established were that our force of gravity is going to come directly down towards the center of the Earth from the center of the object, from its center of mass. And that opposing force on that the table exerts on the book is going to come up, but it's going to come up perpendicular to the surface. And so it's not directly in opposition to gravity. The force of friction on the book is shown this way, parallel to the surface and up the slope. So we're just going to label that force of friction. In the problem in the book, we were given magnitudes, and the force of friction is 11 newtons up the slope. You'll have to pardon the quality of the drawing on my lines. So, with the x-axis tilted to be parallel to the surface of the table, the force of friction lines up directly on the axis. The normal force lines up directly on the y-axis. So neither of those are things that have to be resolved into their components. However, the force of gravity does not line up directly on either of the axes, and in fact has to be resolved into a force of gravity on the y and a force of gravity on the x, f of gy and f of gx. Now this is where we had to get to figuring out this angle. And we did it in class, but I'll just really quickly go through the sort of mini geometric proof one more time. You'll notice that this line that we've made for force of gravity makes a right angle here with the line that's showing what would be the horizontal on the planet, and since this angle is 35, we know that this angle must be 55 degrees because the sum of the interior angles of a triangle are equal to 180. So 180 would equal 35 plus that other angle x, and that angle would equal 55 degrees. So we've established that. So now, looking at that 55, if we momentarily move this line down to there, we can see that there's a 90-degree angle which is formed here, or there would be if my drawing was perfect. Since that's a 90-degree angle, and it's split by the line for force of gravity, the angle on this side must be what? Must be the complement of 55. So that angle is 35. Let's get rid of some of this extra stuff. Now with all that said, you can either go ahead and prove that to yourself every single time, or you can remember that when you've got an object on a sloped surface, this angle is going to be equal to this angle, which is probably the easiest course. So, now that we've done that, now that we did all that, we need to figure out, we're asked for the net force on this. So, the net force is sort of like the net motion or displacement or anything else, where we want to calculate the sum of forces on each axis and see what we have left, and then find a resultant. That's all it is a resultant. So what we're going to do is what's called a sum of forces. And we'll start off with a sum of forces, and we write this sigma symbol, though I've written it badly. We'll start off with the sum of forces on the x-axis. It doesn't matter which axis we start off with. And we know that the sum of forces on the x-axis is going to be equal to the force of friction up the slope plus the force of gravity on the x-axis, which is operating down the slope. You can use left and right. I tend not to. Okay, well that's fine. We're given force of friction. We have to write an expression for force of gravity on the x. So because we know that this angle is 35 degrees, we can write that expression, and the force of gravity on the x is opposite the 35. So f of gx is equal to sine 35 times f of g. Okay. So we've rewritten the sum of forces on the x to read force of friction plus f of gx time, or f of g rather, times sine of 35. So we're now ready to put numbers in. Again, there are different ways. So here we have sum of forces on the x is equal to 11 newtons up the slope plus 12.6186, etc. newtons down the slope. Now, there are different ways to handle this. And if we were calculating the force of gravity ourselves, we'd be entering the negative 9.81 meters per second squared into the equation. We didn't. So, again, knowing that sine acts as a proxy for direction very often, you can either choose to make the larger number here positive, though in this case I actually don't recommend that. I suggest that you make that f of gx on the f of gx your negative number, so you would end up with a sum of forces on the x of 11 plus a negative 12.6186, which gives you a sum of forces on the x of negative 1.61868, etc. newtons, of course. Well, now we need to do sum of forces on the y, though in a very real way, that should be fairly obvious to you. Let's shrink all of that. So when we are doing our sum of forces on the y-axis, the two forces that we have on the y-axis are what? Well, we have our normal force, which is up, and our force of gravity on the y, which is of course down. So using that 35-degree angle, of course we know that force of gravity on the y is adjacent to the angle, so the expression for force of gravity on the y is going to be f of g times cosine of 35. And that's definitely going to be negative. It's, even if we use a traditional Cartesian coordinate system, it lines up the same way. Now, I say that this one should kind of be a cheater for one reason. Pardon my little arrow, it's pretty crooked. Is this object rising up into the air or sinking down through the table? If the answer is no, you know that the sum of forces on the y is equal to 0. So, because the only force upward on the y-axis is that 18 newtons, we could almost say we know already what the force of gravity on the y is going to be. But because this is physics, we're going to calculate it. So we have 18 newtons, and when we compute force of gravity on the y, force of gravity times cosine 35, we get, no great surprise, 18.021, etc. newtons. So what your book does is actually to round that 18 before it gets there. So they say, oh, these are equal. It's 18 and 18. So sum of forces on the y is equal to 0. We'll do that here because otherwise this book would be sinking down through the table, and it's not. In reality, what they've done is used bad sig figs here And we know that the sum of forces, or that the normal force on the book is identical to whatever the force of gravity on the y-axis is. So, using their sort of sloppy math, we now can say that we know the net force on the book. It's not on the y-axis. The net force is all on the f-axis. So, the net force on the book, well, again, with that sign and direction proxy, we say it's equal to negative 1.6186, etc., and we have two sig figs, so this would be equal to negative 1.6 newtons. We can say negative, or we can say down slope. Your book uses it uses 2 newtons because the sig figs are terrible. So it would be saying 1.6 newtons on the positive x-axis. And while that's true, what that doesn't convey is the fact that you have an unbalanced force down the hill. This book is going to slide. So I think it's more useful to say that the net force, and you wouldn't put this on your force diagram, I'm just doing it to demonstrate. Your net force is equal to negative 1.6 newtons. And that conveys the information that this thing is going to start to slide down the table. Okay, with every single net force problem, these are general tips. You start off with a sum of forces on each axis and go from there. So for today, your assignment is problems number 1 through 4 on page 133. These are the 4A practice problems. Okay, so you'll get a start on those, and when I come back on Tuesday, we will start with some 4B problems. Okay, get going.